Hello everyone and welcome back. So today we're going to be going over the equations of motion. We're going to be focusing on rectangular coordinates and also hitting on the normal and tangential coordinate system. Now, unlike most times, we're not going to have examples at the end. I'm actually going to intersperse those in between our various sections because there's a whole lot here and I want to make sure that you get an example for all of them. So let's jump right into it. Now, why do we care about these equations? What matters? Well, let's look at this guy right here. Let's say he's pushing with a force of, force F, and it's a 100-pound crate. Now, how large of a force does he have to actually apply before the crate will start moving? And what factors influence that? And if the crate starts moving, is their acceleration? Will it just be constant? No velocity? Will accelerate initially and then kind of level off? What would you have to know before you could find these answers? Well, one of them was probably friction, as we're going to see later. Or this vehicle right here. Now, this drag racer obviously doesn't run with that parachute the entire time. It's only when they get to the end of the track that they deploy the parachute. And that parachute inflicts a drag force. And that drag force is a function of velocity. So if we know what the dragster's velocity is, and we know the magnitude of the opposing drag force, could we figure out how long or how far it's going to take before that drag racer can actually come to a complete stop? How will we do that? Well, these are all questions that we're going to begin to answer today. So our best equation of motion is simply force equals mass times acceleration. It's best when we have to find forces, especially if those forces are perpendicular to the path. Remember, our unbalanced forces will cause acceleration. Unbalanced forces will cause acceleration. Now, we can write three scalar equations from this one vector equation. And we can break them into their Cartesian or rectangular coordinate system. So we have our vector equation, and what we realize is that the force in the x direction is going to be proportional to the acceleration in the x direction. Force in the y to the y. Force in the z to the acceleration in the z. Or we get them as these three scalar equations right here, getting rid of all of our i's, j's, and k's. Now, at any particular point in time, this will be true. So how would we solve these kinds of problems? Well, first thing you're going to do is draw a free body diagram. It's always critical. You're going to establish your coordinate system and then draw that particle's free body diagram showing only the external forces. Remember, we don't show internal forces. If it's a big ball of gas, you don't talk about how all those gases are bumping into each other. That doesn't matter. Then you have to include things like the weight, or normal forces, friction, applied forces, and you want to show where it's going to be going. Because this is going to be helpful as a sanity check. What direction is it moving? If you say it's going to be going this direction, and you know it's going to be going that direction, but your forces in the end are pointing that direction, well, something went horribly wrong. So, while I don't necessarily like kinematic diagrams, they do have a point in that they help you to check and make sure that your answers make sense. Also, make sure that any frictional forces act opposite to the direction of motion. And sometimes you won't know. You won't know what direction it's going to move, and you'll have to guess and try it both ways. And finally, if you're connected to a spring, the force is always going to be resisting whatever direction you're stretching that spring or compressing that spring. Then you draw your equations of motion. So if our forces can be resolved directly from our free body diagram, well, then we can use our scalar equations of motion. In more complex cases, usually 3D ones, we'll have to use some vector analysis. I like breaking things into components. That's the way that makes the most sense to me, but use what works for you. So don't forget this. You have three equations, one for the forces on the x, the y, and the z, and this is there to help you. Because If we know what the acceleration is and we know the right direction the acceleration is, then we can find out what some of the forces would have to be to provide that acceleration. Now, as a note, in a lot of cases we're two-dimensional and this third one will fall off, so we only have two equations, but who cares? It makes things simpler on you. Now, after you've done that, you're like, oh my goodness, this procedure takes forever. It really does. It's a long procedure. We go into our kinematics. That second law only provides solutions for forces and our accelerations. If we want velocity or position, well, then we're going to have to use our kinematics equations. So like I've said before, and I'll say it again, you never get to forget kinematics. You will still be using this in the very last chapter. So you might have to pull on any of the ones you've learned from chapter 12 to solve your problems. So make sure that you're consistent about what the positive coordinate direction is, because that will really mess you up if you aren't. Okay, so we'll stop here, and then next time we're going to jump into an example to show you how to do this. So thank you for listening, and I'll see you all next time. Bye-bye.